Okay, so this video is for my future self so that I don't get confused about light. Specifically, we're going to talk about reflection, refraction, absorption, transmission, and all of that. So, to begin with, let's talk about light. So, light, in terms of classical physics, is an electromagnetic wave. Essentially, it's got two components. One is the electric field, and the other is the magnetic field. Okay, so these two components are perpendicular to each other at all times, right? So that is light. Now, don't get confused about whether light is so, because the electric field, it creates a magnetic field, and then the magnetic field creates another electric field, and then that creates a magnetic field. That is not what happens. Okay, what happens is that there is a source charge which we can consider to be an electron. An electron, say, is oscillating back and forth, or let's just consider the case of an electron, going forward or going upward, right? So initially, this is what the field lines look like, right? They're all pointing towards the electron, and once the electron reaches this point, its field lines look something like this. So it's still in this line. Let's say this is where the electron has reached. Now its field lines point here, right? So this happens in some amount of time, and if we think about the field lines, right, they have to be continuous everywhere, right? There have to be some electric fields somewhere in the world. So what happens is, because this has moved from this to this, there must be, while the electron is moving upwards, some kink as to, where the electric field was here, and then it moved there, and now this is where the electric field is, or something like this. But the major point is that there has to be a kink, right? In other words, electron here, right, we have the electric fields pointing inwards. The electron then moves here, right, and now the electric fields are pointing this way, and so there must be some time in which there has to be a kink about the information of the electron moving upwards that is propagating outwards, and we define this speed to be c, which we'll notice after, I guess, a few videos, that this speed c is the speed of light. So currently we're just defining the speed of light to be the speed in which this information about the traveling of the electron is reaching outwards through the propagation of a disturbance in the electric field of the electron. Okay, so there's the electron, we disturb the electron upwards, and so the field moves upwards, and eventually this kink will move here, 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 and it will propagate out. This information will propagate out. Now let's consider the case of an electron moving upwards and downwards. If it moves upwards, the kink moves here, and if it moves downwards, the kink goes on this way, and over time it creates an electric field. Okay, it creates an electric field. Aha, now we have the electric component of our electromagnetic wave. But according to Maxwell's laws, Maxwell's equations, whenever there is a changing electric field, there is a changing there is a magnetic field. So you had an electron, which is a charged particle, which is accelerating, and so you have an accelerating, a changing electric field over time. And what happens is that this changing electric field, it generates a magnetic field that is perpendicular to the electric field. And so because of this, uh, considering this is downwards motion, we have a magnetic field which looks something like this. Okay, so it's kind of pointing inwards. That's what the magnetic field looks like, and the electric field, that is what the electric field looks like. Okay, so do not confuse it with this, that okay, there's an electric field generates a magnetic field that generates an electric field. No, that is not the case. That's not the point. The point is that an electric field, a propagating electric disturbance, is created by the same source that a magnetic field is created. And so whenever there is a disturbance in the electric field, there will be a magnetic field accompanying it, right? That's the entire point. So whenever there is an accelerating charge, there is an EMW. So now that that is clear, let's look at what happens to the photon or the light. Let's stick with light. What happens to the EMW when it reaches a medium? So because we're out of the way that okay, this is just electric and magnetic fields propagating outwards. Let's just consider the electric field part, right? So here's our electric field, and this encounters a medium, and the medium has this electron that is here. So it comes here and it reaches this electron, and this electric field, it's kind of like this collection of field vectors, right? So at any moment of time, say you have this point, this is the electric field. So as soon as it reaches here, you have the electric field is just a force per coulomb, and so you have a force experienced by a charge q that is scaled to the electric field intensity at that point. So it reaches here, and so the electron is now in an electric field. As soon as the field reaches here, there is the field vector that is pointing here, and so the electron will experience a force downwards. As a result, there will be its own oscillation as the field moves forward in time. Right, as the field moves forward in time, the electron will start oscillating back and forth, creating its own field, which would be, if I'm not wrong, I might be wrong if it's in the same phase or not, but I guess it's pi by 2 off. It's half a time period off. Oh no, not half, but 1/4 of the time period off. Right? If it's a sine wave coming in, this will create a cos wave. I think that's it. So what moves forward is actually the superposition of the incident field and the electron's little induced electric field, right? That's what propagates forward, and that is the concept of light's interaction at the interface of a medium, right? So let's look at different cases here, right? So just to give you a rough idea, currently, because there is an electric field, there will be some electric field that is generated and that will reflect back into the source medium, and then there is some that propagates forward along with the incoming incident electric field, which will superpose and create the refracted field. So that's the refracted field, that's the reflected field. And finally, we have something crazy that is about to happen, that because these electrons are moving, they might bump into other electrons, and what they have is they don't really emit electrons, and they don't really emit photons right out of the way, but they dissipate their kinetic energy or their oscillatory energy to nearby electrons and molecules. And what happens is that overall, instead of fluorescence, there is heat dissipation called internal conversion. That's what I looked up. I'll link all the videos if I'm uploading this on the web. So there's internal conversion of this energy, right? So the incident photon, it comes in and it dissipates as heat. That's the third way. And because it dissipates at heat, it increases the temperature of the substance, and instead of reflecting back the same kind of wavelength, what is emitted rather, um, is something of a different wavelength, right? So there are different laws that is governing all of these. What proportion will the light reflect, refract, or get absorbed? But yeah, it's essentially just the induced EMF that is produced within the electron, interacting with whatever the incident electron and whatever the incident electric field is, that will generate um, a superimposed refracted wavelength that is propagating, or it might re-emit and reflect a field that is propagating in the same medium as was incident, or it might dissipate as what happens in melanins in our body, right? Melanin, rather, I think that is plural. It's just this protein or whatever it is. It's an organic compound that dissipates heat and avoids mutation. So that's kind of cool, and I'll cover that aspect in a bit. But currently, just to give a broad view of this is how things happen. And I want to finish out. Okay, I'll do it in the next video.